Tonight, we're going to explore a measurement that sounds deceptively simple, but reveals one of the most profound truths about reality: light years. Astronomers use it constantly when talking about the distances to stars and galaxies. But here's what's going to change everything for you tonight. A light year isn't just a way to measure how far away something is. It's a measurement that proves distance and time are the same thing. And once you understand what a light year really means, you'll realize something extraordinary. The universe you see when you look up at night doesn't exist. Not anymore. Every point of light in the sky is showing you the past, and the farther away something is, the deeper into history you're looking. And by the end of tonight, you're going to understand why astronomers had no choice but to invent this measurement, how it reveals that the night sky is actually a museum of cosmic history, and why looking across space always means looking backward through time. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something you experience every single day, but probably never think about. Light has to travel. This seems completely obvious when you say it, but most people live their entire lives without considering what this actually means. Right now, you're watching this video on a screen. Light from that screen is traveling to your eyes. That journey takes time. Not much time, obviously. The distance from your screen to your eyes is maybe 18 inches, maybe 2 feet. Light crosses that gap in about 2 billionths of a second. Far too fast for you to perceive. Your brain processes it as instant, but it's not instant. There's a delay, microscopic but real, between when the light leaves the screen and when it enters your eye. During that infinitesimal moment, time passes. The photons are in transit, carrying information about what's on your screen. By the time they reach you, that information is already old. 2 billionths of a second old, but old nonetheless. Now, let's scale this up. The sun is our closest star, the source of all light and heat that makes life on Earth possible. We see it every day, this familiar yellow disk crossing the sky. The sun is 93 million miles away. That's the average distance, what astronomers call 1 astronomical unit. Light from the sun travels at 186,000 miles per second. Nothing in the universe moves faster. At that incredible speed, light still takes 8 minutes and 20 seconds to cross the 93 million miles between the sun and Earth. Think about what this means. When you step outside on a sunny morning and feel warmth on your face, that warmth left the sun 8 minutes and 20 seconds ago. The light, illuminating everything around you, started its journey before you walked outside. You're not feeling the sun as it is right now. You're feeling the sun as it was 8 minutes ago. The sun doesn't change much in 8 minutes. It's been burning for 4.6 billion years. 8 minutes is nothing compared to that immense timescale. The sun you see now looks essentially identical to the sun that exists in this present moment. But the principle is established. There's a gap between when light leaves its source and when you perceive it. That gap is filled with time. And the farther away the source, the larger that gap becomes. Let's go farther. Mars, when it's at its closest approach to Earth, is about 34 million miles away. Light from Mars takes about 3 minutes to reach us. When astronomers look at Mars through telescopes, they're seeing Mars as it was 3 minutes ago. If a dust storm started on Mars right now, we wouldn't see it for 3 minutes. The information travels at light speed, but light speed is finite. Jupiter, the giant of our solar system, orbits much farther out. When Jupiter is closest to Earth, it's about 390 million miles away. Light takes about 33 minutes to cross that distance. If Jupiter suddenly exploded right now, we wouldn't see it for half an hour. The last light from intact Jupiter would keep arriving for 33 minutes. Only then would we see the explosion. Neptune, the most distant planet in our solar system, is about 2.7 billion miles away. Light from Neptune takes about 4 hours to reach Earth. When you look at Neptune through a powerful telescope, you're seeing it as it was 4 hours ago. Early afternoon, if you're observing at night. The Neptune you see is from when you were still at work, or eating lunch, or sitting in school. But Neptune is still in our solar system. It's our cosmic neighbor, relatively speaking. When we venture beyond our solar system to the nearest stars, the time delays become measured not in minutes or hours, but in years. And this is where we need a new unit of measurement. This is where the light year becomes necessary. A light year is exactly what it sounds like. The distance light travels in 1 year. Light moves at 186,000 miles per second. Every second, photons cross 186,000 miles of space. In 1 minute, that's about 11 million miles. In 1 day, about 16 billion miles. In 1 year, light travels approximately 5.88 trillion miles. That's 1 light year. 5.88 trillion miles. Now, why do astronomers use this unit? Why not just stick with miles? Because miles become completely useless when you're measuring cosmic distances. The numbers get so large, they lose all meaning. They become abstract symbols that your brain can't process in any meaningful way. Let me show you. Alpha Centauri is the nearest star system to our Sun. It's actually a triple star system, 3 stars orbiting each other. The distance to Alpha Centauri is about 25 trillion miles. Does that number mean anything to you? Can you visualize 25 trillion miles? Can you compare it to other distances in any intuitive way? Probably not. Your brain just sees it as a really big number. But if I tell you Alpha Centauri is 4.37 light-years away, that's cleaner. You can compare it to other distances. If one star is 4 light-years away and another is 40 light-years away, you immediately know the second is 10 times farther. The numbers stay manageable. And here's the beautiful part. Light-years inherently connect distance and time. When you say something is 4 light-years away, you're simultaneously saying the light you see left that object 4 years ago. Distance equals time. They're the same measurement. This is why light years are so powerful. They don't just tell you how far something is. They tell you when you're seeing it from. Alpha Centauri, 4.37 light-years away, means you're seeing it as it was 4.37 years ago. The light entering your eye tonight left that star system over 4 years in the past. If someone on a planet orbiting Alpha Centauri pointed a telescope at Earth right now, they'd see Earth as it was 4.37 years ago. They'd see people, cars, cities, as they existed back then. They wouldn't see the present. They couldn't. The light from our present hasn't reached them yet. It's still traveling through space, crossing the 4.37 light-years between us. Let's explore more stars and watch the time delay grow. Tau Ceti is a star similar to our Sun. It's 11.9 light-years away. The light you see from Tau Ceti left that star nearly 12 years ago. If you're 25 years old, that light started its journey when you were 13, probably in middle school. If you're 40, it left when you were 28. Epsilon Eridani is another nearby star, about 10.5 light-years away. The light you see tonight left that star over a decade ago, before smartphones looked like they do now, before certain apps existed, before recent historical events occurred. You're seeing a star from a different era of human history. Not ancient history, but different nonetheless. Fomalhaut, the brightest star in the constellation Piscis Austrinus, is 25 light-years away. That light began its journey a quarter-century ago. If you're 30, it left before you were born. The photons hitting your retina tonight have been traveling through empty space longer than you've been alive. Pollux, one of the twin stars in Gemini, is 34 light-years away. The light you see is from 34 years ago. If you're younger than 34, every photon from Pollux is older than you are. Regulus, the brightest star in Leo, is 79 light-years away. The light you see tonight left Regulus in 1945. World War II was ending. The atomic bomb had just been used. The United Nations was being founded. That's when this light began its journey. It's been traveling for 79 years, crossing the vast emptiness between Regulus and Earth. And it arrived tonight, entering your eye, showing you a star from 1945. Spica, the brightest star in Virgo, is about 250 light-years away. The light you see left Spica around 1774. The American Revolution hadn't happened yet. George Washington was 42 years old, not yet famous. The Declaration of Independence wouldn't be signed for another 2 years. Mozart was 18 years old, just beginning his career. That's the world that existed when this light left Spica. And you're seeing it now, in the 21st century, 250 years later. Alkaid, the star at the end of the Big Dipper's handle, is 104 light-years away. That light is from 1920. The Roaring Twenties. World War I had just ended. The League of Nations was being established. Radio was becoming popular. Television didn't exist yet. That's when Alkaid's light left. It's been traveling ever since, and it's arriving at Earth right now. Capella is actually a system of 4 stars that appear as one bright star in the constellation Auriga. It's 43 light-years away. The light you see tonight is from 1981. The first space shuttle had just launched. MTV had just started broadcasting. The internet, as we know it, didn't exist yet. Cell phones were rare, bulky devices few people owned. That's the era you're seeing when you look at Capella. Mizar and Alcor, the famous double star in the Big Dipper, are about 83 light-years away. The light you see is from 1941. World War II was raging. The attack on Pearl Harbor happened that year. The United States entered the war. That's when this light left those stars. Everything that's happened since, the entire post-war era, the Cold War, the space age, the digital revolution, all of it occurred while this light traveled to Earth. Now let's go much farther. Antares, the red supergiant in Scorpius, is about 550 light-years away. The same distance as Betelgeuse, actually. The light you see from Antares, tonight, left in the year 1474. Christopher Columbus was 23 years old. He hadn't sailed to the Americas yet. The printing press had only been invented recently. The Renaissance was underway in Italy. The Aztec Empire was flourishing in Mexico. The Inca Empire was expanding in South America. That's Earth, in 1474. And the light from Antares has been traveling toward us ever since. For 550 years, crossing the immense distance between that star and our solar system. Canopus, the second brightest star in our entire night sky, visible from the southern hemisphere, is about 310 light-years away. The light you see left Canopus in 1714. Queen Anne ruled England. Louis XIV, the Sun King, was King of France in the final year of his life. Peter the Great ruled Russia. The Qing dynasty controlled China. Benjamin Franklin was 8 years old. That's when this light began its journey, 3 centuries ago. Rigel, the bright blue star marking Orion's foot, is about 860 light-years away. That light is from 1164, the Middle Ages. The Crusades were ongoing. Genghis Khan was uniting the Mongol tribes. Gothic cathedrals were being built across Europe. Universities were just being founded. That's more than 8.5 centuries ago. And the light from Rigel has been traveling all that time. Polaris, the North Star, is actually about 430 light-years away. That light is from 1594. Shakespeare was 30 years old, having just established himself as a playwright. Galileo was 30, teaching mathematics, 10 years before he'd build his first telescope. The scientific revolution was beginning. The light you use to navigate, the star that marks north, is showing you the late 1600s. Deneb, one of the most luminous stars in our galaxy, is about 2,600 light-years away. That light left Deneb around 400 BCE. Ancient Greece was entering its golden age. Socrates had recently died. Plato was running his academy in Athens. Aristotle was young. The Parthenon had been completed only about 50 years earlier. Alexander the Great wouldn't be born for another 20 years. That's the world that existed when Deneb's light began its journey, 2,600 years ago. Everything that's happened in Western civilization since then, the rise of Rome, the spread of Christianity, the Middle Ages, the Renaissance, the Age of Exploration, the Industrial Revolution, 2 world wars, the Atomic Age, the Space Age, the Information Age, all of it occurred during the time this light has been traveling to Earth. Every star you can see with your naked eye is showing you the past. The nearby stars are showing you the recent past, years or decades ago. The more distant stars are showing you centuries or millennia ago. When you look up at the night sky, you're not seeing one moment in time. You're seeing thousands of different moments spread across history. Each star is frozen at a different point in the timeline. Some from when you were a child, some from before you were born, some from before your grandparents were born, some from before nations existed, some from before recorded history, all visible simultaneously, creating this tapestry of time spread across the darkness. The night sky is not a snapshot. It's a timeline. Now, let's venture beyond individual stars to entire galaxies. The Andromeda galaxy is the nearest major galaxy to the Milky Way. It's 2.5 million light-years away. 2.5 million years. The light you see from Andromeda left that galaxy 2.5 million years ago. When that light began its journey, humans, as we know them, didn't exist. Homo sapiens hadn't evolved yet. Our ancestors were early members of the genus Homo, primitive humans with smaller brains, just beginning to make simple stone tools. They couldn't speak. They had no art, no culture, no abstract thought, as we understand it. They were surviving in East Africa, barely recognizable as our ancestors. That's Earth, 2.5 million years ago. And the light from Andromeda has been traveling toward us for all that time, across the vast intergalactic void, and it's arriving now, showing us Andromeda from the deep past. The Andromeda we see doesn't exist anymore, not in that form. In 2.5 million years, stars have been born and died. The galaxy has rotated. Its spiral structure has evolved. But we can't see any of that. We can only see how it was 2.5 million years ago. The Triangulum Galaxy, another member of our local group, is about 3 million light-years away. The light you see is 3 million years old. Our ancestors then were Australopithecus, ape-like creatures that walked upright but had brains only slightly larger than chimpanzees. They couldn't make fire. They couldn't build shelters. They were scavengers and gatherers, living day to day. That's how primitive Earth was when that light left Triangulum. The Sombrero Galaxy is about 31 million light-years away, 31 million years in the past. The Oligocene epoch. Mammals dominated the planet. Early primates were evolving. Grasses were spreading across the continents, creating vast savannas. Antarctica was beginning to freeze over. The climate was warmer than today. That's Earth, 31 million years ago. The entire evolutionary history of humans, from primitive primates to Homo sapiens, happened during the time this light has been traveling. The Virgo cluster is a massive collection of about 1,500 galaxies. It's about 54 million light-years away. 54 million years. The Paleogene period. Dinosaurs had been extinct for about 10 million years. Mammals were diversifying rapidly, filling ecological niches left empty by the dinosaurs. Early whales were evolving from land mammals. Primates were small, tree-dwelling creatures. India had recently collided with Asia, creating the Himalayas. That's when the light from the Virgo cluster galaxies left, 54 million years ago. Everything that's happened on Earth since then, the evolution of countless species, the shifting of continents, the rise of grasslands, the appearance of great apes, the evolution of humans, all of civilization, all of recorded history, all of it is more recent than the light you see from these galaxies. The Coma cluster is about 320 million light-years away. 320 million years. The late Carboniferous period, transitioning into the Permian, the supercontinent Pangaea was forming. Reptiles were beginning to dominate the land. The first seed plants were evolving. Vast coal forests covered much of the land. Insects were huge. Some dragonflies with wingspans over 2 feet. The ancestors of dinosaurs hadn't appeared yet. That wouldn't happen for another 60 million years. That's Earth, 320 million years ago. And the light from the Coma cluster has been traveling ever since. The Hercules cluster is about 500 million light-years away. 500 million years. The Cambrian explosion had just occurred. Complex life was new. Before the Cambrian, life was mostly simple, single-celled organisms and some basic multicellular forms. During the Cambrian explosion, complex animals suddenly appeared. Creatures with eyes, with skeletons, with complex body plans. Trilobites crawled on the ocean floor. Early arthropods swam in the seas. There was no life on land. Not yet. The continents were barren rock. That's the Earth that existed when the light from the Hercules cluster left, 500 million years ago. Now, let's go to the edge of what we can see. The most distant galaxies observed by telescopes, like the James Webb Space Telescope, are over 13 billion light-years away. 13 billion years. The universe is about 13.8 billion years old. So, we're seeing these galaxies as they were only about 800 million years after the Big Bang. We're seeing the early universe, when the first stars were forming, when the first galaxies were assembling from clouds of hydrogen and helium, before most stars existed, before most galaxies took their current forms. We're seeing cosmic dawn, the moment when the universe first lit up with starlight. And this is only possible because light takes time to travel, because we're always looking into the past. The farther we look, the farther back we see. The universe is showing us its own history, and we can observe it by looking at objects at different distances. Nearby galaxies show us the recent past. Distant galaxies show us the ancient past. Together, they tell the story of how the universe evolved from a hot, dense state after the Big Bang to the structured cosmos we see today. This is one of the most powerful tools in astronomy. We can study cosmic evolution not by theorizing about the past, but by observing it directly. We can see galaxies at different ages by looking at different distances. Young galaxies far away, old galaxies nearby, the entire timeline visible, spread across space. Now, let's think about what this means for specific events. Supernovae are massive stellar explosions. When a giant star runs out of fuel, its core collapses and the star explodes. For a few weeks, a single exploding star can shine as brightly as an entire galaxy. These explosions are rare in any given galaxy. In the Milky Way, they happen about once every 50 years on average. But when we observe supernovae in distant galaxies, we're seeing explosions that happened long ago. In 1987, astronomers observed a supernova in the Large Magellanic Cloud. It was designated SN 1987A. It became one of the most studied supernovae in history. The Large Magellanic Cloud is about 168,000 light-years away. The explosion astronomers observed in 1987 didn't happen in 1987. It happened 168,000 years ago, around 166,000 BCE, when Homo sapiens were just beginning to appear in Africa, when Neanderthals lived in Europe. When the Earth was in the midst of an ice age, that's when the star exploded. The light from that explosion traveled for 168,000 years, and it arrived at Earth in 1987. Astronomers studied it intensely, learning about the physics of stellar explosions. But they were studying ancient history, an event from the deep past, delivered to them by light. In 1994, astronomers observed the collision of a comet with Jupiter. Comet Shoemaker-Levy 9 broke into fragments and slammed into Jupiter over the course of several days. It was spectacular. Jupiter is far enough away that light takes about 40 minutes to reach Earth when the planets are aligned favorably. So when astronomers saw the first impact, it had actually occurred 40 minutes earlier. They were watching history unfold, but on a 40-minute delay. Every observation in astronomy is like this. Every measurement is of the past. The closer the object, the more recent the past. The farther the object, the more ancient the past. There are no observations of the present in astronomy. There can't be. The light hasn't arrived yet. This creates some interesting philosophical questions. When we say a distant galaxy exists, what do we mean? We can see it as it was billions of years ago. But we can't see it as it is now. The current state is unknowable to us. It won't be knowable for billions more years when the light from now finally reaches Earth. So in what sense can we say we know that galaxy? We know its past. We can infer its present based on our understanding of physics and galaxy evolution, but we can't observe its present. From our perspective, the galaxy's present doesn't exist in our observable reality. Only its past exists. This is true for everything in the universe beyond our immediate vicinity. The farther away something is, the less we know about its current state. We can see where it was, but not where it is. We're surrounded by history, ancient light carrying information from the past. And that's all we can ever see. The present is invisible, hidden behind the light travel time barrier. Let's think about communication across cosmic distances. If we ever detect a signal from an extraterrestrial civilization, that signal will be from the past. If the signal comes from a star 100 light-years away, it was sent 100 years ago. By the time we receive it, a century will have passed for them. If we reply, our response will take another 100 years to reach them. 200 years for one exchange. The civilization that sent the original message might not even exist anymore by the time our reply arrives. They might have gone extinct. They might have transcended biological existence. They might have colonized other star systems and moved on. 200 years is long enough for civilizations to change beyond recognition. And that's for a relatively nearby star. For a civilization 1,000 light-years away, one exchange would take 2,000 years, longer than recorded human history. The people who sent the message and the people who received the reply would be separated by 2,000 years of history. They'd be as different as ancient Romans are from modern humans. Probably more different. This is the barrier that light speed creates. It doesn't just separate us in space. It separates us in time. Any interstellar communication would be an exchange of historical records, not a conversation. You wouldn't talk to aliens. You'd send messages to their past and receive messages from their past. The present would never align. Now let's talk about what this means for the cosmic microwave background. The cosmic microwave background, or CMB, is radiation left over from the Big Bang. It's the oldest light in the universe. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that, the universe was too hot. It was a plasma of charged particles. Light couldn't travel freely because it kept scattering off the charged particles. But when atoms formed, the universe became transparent. Light could suddenly travel without scattering. This is called the surface of last scattering. The photons released at that moment have been traveling through space ever since, and they're still arriving at Earth today. That's the cosmic microwave background. When we detect the CMB, we're seeing light from 380,000 years after the Big Bang, about 13.8 billion years ago. We're seeing the early universe directly, before stars existed, before galaxies formed. Just a hot, dense, nearly uniform soup of hydrogen and helium beginning to cool. The CMB is the ultimate example of looking into the past. It's the oldest light we can see, the earliest image of the universe accessible to us, and it's only visible because light takes time to travel. The CMB shows us tiny temperature variations across the sky. Some regions are slightly hotter, some slightly cooler. These variations are incredibly small, only about 1 part in 100,000. But they're crucial because they show us the seeds of cosmic structure. The slightly denser regions would eventually collapse under gravity to form the first stars and galaxies. By studying the CMB, we're seeing the origins of everything. The patterns that would become galaxies, clusters, superclusters, the entire large-scale structure of the universe, all visible in this ancient light from 13.8 billion years ago. Now, let's think about the future. As technology improves, we'll build more powerful telescopes, we'll see farther into space, and therefore farther into the past. The James Webb Space Telescope can see galaxies from when the universe was only a few 100 million years old. Future telescopes might see even farther back, maybe to when the universe was only 50 million years old, or 20 million years old, the very first stars forming from primordial gas. Each new generation of telescopes is a more powerful time machine, each one giving us access to earlier eras of cosmic history. But there's a limit. We can never see before the surface of last scattering. Before 380,000 years after the Big Bang, the universe was opaque. Light couldn't travel freely. So we can't see it with telescopes that detect light. That era is hidden from us, at least from optical observation. We might be able to study it using gravitational waves or neutrinos, which can pass through the opaque early universe. But we can't see it with light. The CMB is a wall beyond which we cannot see. Still, that gives us access to almost the entire history of the universe, from 380,000 years after the Big Bang to today. 13.8 billion years of cosmic evolution, all visible by looking at objects at different distances, all revealed by the fact that light takes time to travel. Let's bring this back to a human scale one final time. Tonight, go outside and look up at the stars. Really look at them. Think about what you're seeing. That bright star over there might be Arcturus, showing you light from 37 years ago. That one might be Vega, from 25 years ago. That constellation, Orion, contains Rigel, showing you light from over 800 years ago. Every point of light is a different moment in time. Some recent, some ancient, all visible at once. The sky is not just space spread out before you. It's time spread out before you. A visual representation of history. The farther your gaze travels, the deeper into the past you see. And this is only possible because of light years. Because distance and time are connected by the speed of light. Because measuring how far away something is simultaneously tells you how long ago you're seeing it from. This is what a light year really means. Not just a big distance, but a connection between space and time. A measurement that reveals the universe's deepest truth. That we are always, inevitably, looking into the past. That the present is invisible except in our immediate surroundings. That the cosmos is showing us its history, written in light, delivered across space, arriving at our eyes as messages from the past. Every star is history. Every galaxy is history. Every photon is a messenger from a time that no longer exists. And we're here to receive those messages, to decode them, to understand what they're telling us about the universe and our place in it. But let's go deeper into what this means. Let's explore more stars, more distances, more moments frozen in time by the speed of light. Aldebaran is the bright orange star that marks the eye of Taurus the Bull. It's 65 light-years away. The light you see tonight left Aldebaran in 1959. Eisenhower was president. Alaska and Hawaii had just become states. The first microchip had just been invented. NASA was 1 year old. The space age was just beginning. No human had been to space yet. That would happen in 1961. The Beatles were still teenagers, playing in small clubs in Liverpool. That's 1959. That's when this light left Aldebaran. It's been traveling for 65 years. Achernar, one of the brightest stars in the southern sky, is about 140 light-years away. That light is from 1884, the Victorian era. The light bulb had been invented 5 years earlier. The telephone was only 8 years old. Automobiles didn't exist yet. Airplanes were still 2 decades away. Most people traveled by horse and carriage. The world was on the cusp of massive technological change, but hadn't experienced it yet. That's the world when this light left Achernar. 140 years ago. Hadar, also called Beta Centauri, is about 525 light-years away. The light you see is from around 1500, the turn of the 16th century. Leonardo da Vinci was 48 years old at the height of his career. Michelangelo was 25, about to begin work on his David. Columbus had just completed his 4th and final voyage to the Americas. The age of exploration was beginning. The Protestant Reformation was still 17 years away. That's 1500, when Hadar's light began its journey, over 5 centuries ago. Castor, one of the twin stars in Gemini, is about 51 light-years away. The light you see left in 1973. Watergate was dominating American news. The Vietnam War was ending. The first handheld mobile phone call was made that year. Personal computers didn't exist yet. The internet was a small military research project. That's 1973. 51 years ago. Bellatrix, the bright star on Orion's shoulder, is about 250 light-years away. That light is from 1774, the same year as Spica. The American colonies were 1 year away from declaring independence. Captain Cook was exploring the Pacific. The Industrial Revolution was just beginning in England. The modern world was starting to take shape. That's when this light left Bellatrix, 2.5 centuries ago. Alnilam, the middle star in Orion's belt, is about 2,000 light-years away. 2,000 years. The light you see is from around the year 24 CE, the Roman Empire under Tiberius. Jesus had recently been crucified, probably just a few years before this light left. Christianity was a tiny new sect. Rome controlled most of Europe, North Africa, and the Middle East. China was in the Han dynasty. That's 2 millennia ago. And this light has been traveling ever since. For 2,000 years, crossing the vast distance between Alnilam and Earth, arriving tonight, showing you a star from the time of ancient Rome. Alnitak, another star in Orion's belt, is about 815 light-years away. That light is from around 1209, the Middle Ages. Genghis Khan was about to launch his conquest that would create the largest land empire in history. The Fourth Crusade had just concluded. The Magna Carta wouldn't be signed for another 6 years. Gothic architecture was spreading across Europe. That's over 800 years ago. Mintaka, the third star in Orion's belt, is about 915 light-years away. That light is from around 1109, the High Middle Ages. The First Crusade had just succeeded in capturing Jerusalem. Universities were being founded in Europe. The Song dynasty flourished in China. The Khmer Empire was building Angkor Wat. That's over 9 centuries ago. When you look at Orion's belt, you're seeing 3 different moments in history. Al-Nilam, from 2,000 years ago. Al-Nitak, from 815 years ago. Mintaka, from 915 years ago. 3 stars that appear to be in a line, all at the same distance from our perspective, but they're not. They're at vastly different distances, showing us vastly different eras. This is true for every constellation. The stars that form the patterns we see are not physically associated with each other. They're at different distances, different ages, different times. They only appear to form patterns from our vantage point on Earth. From somewhere else in the galaxy, the constellations would look completely different. The stars would be arranged differently. Different patterns would emerge. But from Earth, we see these familiar shapes. And each star in those shapes is showing us a different moment in time. The Big Dipper, for instance. Alkaid at the end of the handle is 104 light-years away. Mizar, the middle of the handle, is 83 light-years away. Alioth, the first star of the handle, is 81 light-years away. Megrez, where the handle meets the bowl, is about 80 light-years away. The stars of the bowl are at different distances too, each one showing us a different year. When you see the Big Dipper, you're seeing a composite image of stars from different decades. The shape you see doesn't actually exist in space. It's an illusion created by our viewing angle and the different distances of the stars. And it's an illusion that changes over time, not on human timescales, but on timescales of tens of thousands of years. The stars are all moving through space at different velocities. Eventually, the Big Dipper will no longer look like a dipper. The stars will drift apart, the pattern will dissolve, and new patterns will emerge. But for now, for our brief human timescale, the Big Dipper looks like a dipper, and each star in it is showing us the past. Let's think about variable stars. Some stars change brightness over time. Cepheid variables are stars that pulsate, expanding and contracting rhythmically. As they pulsate, their brightness changes. Delta Cephei, the prototype of this class, is about 890 light-years away. When you observe Delta Cephei and measure its pulsations, you're measuring pulsations from 890 years ago. The star is still pulsating today, right now, but you can't see those current pulsations. You're seeing the pulsations from the 13th century. The current pulsations won't be visible from Earth for another 890 years. This becomes important for measuring cosmic distances. Cepheid variables have a relationship between their pulsation period and their intrinsic brightness. Longer period means brighter star. By measuring the period, you can determine how bright the star actually is. Then, by comparing that to how bright it appears from Earth, you can calculate the distance. But you're always measuring the past. You're determining the distance to where the star was when the light left, not where it is now. For nearby Cepheids, this doesn't matter much. The star hasn't moved significantly in the time it took light to reach us. But for Cepheids in distant galaxies, millions of light-years away, the galaxy has moved during that time. Space itself has expanded, The galaxy is farther away now than it was when the light left. Cosmologists have to account for this when calculating distances to faraway objects. They have to consider both the light travel time and the expansion of space during that time. It gets complicated. But the fundamental principle remains the same. We're always seeing the past. Now let's think about supernovae again, but from a different angle. When a massive star explodes, it briefly outshines its entire galaxy. A single star releasing as much energy in a few weeks as the Sun will release in its entire 10 billion-year lifetime. These explosions are visible across vast distances. We can see supernovae in galaxies hundreds of millions of light-years away. But every supernova we observe happened long ago. The explosion is ancient history by the time we see it. In 2006, astronomers discovered an extraordinarily bright supernova in a galaxy called NGC 1260. It was designated SN 2006J. It was one of the most luminous supernovae ever observed. NGC 1260 is about 240 million light-years away. The supernova happened 240 million years ago, the Triassic period. Dinosaurs were just beginning to appear. Early dinosaurs were small, about the size of dogs or turkeys. The first mammals were tiny, shrew-like creatures. Pangaea was still intact, one supercontinent. That's Earth, 240 million years ago. And somewhere in a distant galaxy, a massive star exploded. The light from that explosion traveled through space for 240 million years, crossing the vast distance between that galaxy and the Milky Way, and it arrived at Earth in 2006. Astronomers detected it, studied it, learned from it. But the explosion they were studying happened before dinosaurs ruled the Earth, before the Atlantic Ocean existed, before the Rocky Mountains formed. Ancient history on a cosmic scale. In 2011, astronomers discovered SN 2011 Phae, a supernova in the nearby galaxy M101. M101 is about 21 million light-years away. The supernova that astronomers observed in 2011 happened 21 million years ago, the Miocene epoch. Early apes were living in Africa. The ancestors of orangutans, gorillas, chimpanzees, and humans were diverging. Grasslands were spreading across the continents. The climate was warmer than today. That's when this star exploded, 21 million years ago. The entire evolution of the great apes, including humans, happened during the time this light traveled to Earth. When astronomers study these supernovae, they're studying stellar physics. They're learning how stars explode, what elements are created, how the energy is released. But they're studying it through observations of events from millions of years ago. The stars that exploded don't exist anymore. They left behind neutron stars or black holes. The remnants have evolved for millions of years. But we're seeing the moment of explosion, frozen in time, delivered to us by light. This is the nature of astronomical observation. Everything is historical. Everything is a recording from the past. Let's think about quasars. Quasars are incredibly bright objects powered by supermassive black holes in the centers of galaxies. Material falling into these black holes heats up and emits enormous amounts of energy. A single quasar can outshine 1 trillion stars. All quasars are very far away. The nearest is about 600 million light-years distant. Most are billions of light-years away. When we observe quasars, we're seeing the early universe. Quasars were much more common billions of years ago than they are today. This tells us something important about cosmic evolution. In the early universe, galaxies were forming, merging, growing. Their central black holes were actively feeding. As the universe aged, galaxy mergers became less common. Black holes ran out of nearby material to consume. Quasars became rare. We see this evolution directly by looking at different distances. Distant quasars, showing us the universe billions of years ago, are common. Nearby galaxies, showing us the recent universe, rarely have quasars. The quasar era has mostly ended. We're living in a quieter time, cosmically, but we can still see that earlier, more violent era by looking far enough away, by looking far enough into the past. 3C 273 is one of the brightest quasars. It's about 2.4 billion light-years away. The light you see left 3C 273 2.4 billion years ago. The Proterozoic eon on Earth. Life was single-celled. Bacteria and archaea dominated. Eukaryotic cells, the complex cells that would eventually give rise to plants and animals, were just evolving. Oxygen was accumulating in the atmosphere. The Earth was transforming from an anaerobic world to an aerobic one. Complex life didn't exist yet. That's Earth, 2.4 billion years ago. And the quasar 3C 273 was blazing brightly in a distant galaxy. That light has been traveling ever since, across billions of light-years of space. And it's arriving now, showing us a quasar from the deep past. The quasar probably doesn't look like that anymore. It's likely faded. Its black hole probably consumed most of the available material and quieted down. But we can't see that. We can only see how it was 2.4 billion years ago. Let's think about galaxy collisions and how we observe them. When two galaxies collide, the process takes hundreds of millions of years. They approach, pass through each other, swing back for a second pass, eventually merge. We can observe galaxies at different stages of this process, but we're always seeing them as they were in the past. The Andromeda galaxies are two spiral galaxies in the process of merging. They're about 45 million light-years away. What we see is the collision, as it was 45 million years ago. The Eocene epoch. Early primates were evolving. Early whales were adapting to ocean life. India had recently collided with Asia. The Himalayas were forming. Antarctica was beginning to freeze over. That's when the snapshot we see of the Andromeda galaxies was created, 45 million years ago. The collision has progressed 45 million years since then. The galaxies might be fully merged by now, or they might still be in the process. We can't know. We won't know for 45 million more years when the light from their current state reaches us. ARC 220 is another pair of colliding galaxies, about 250 million light-years away. The collision we see happened 250 million years ago, the Permian-Triassic boundary. The worst mass extinction in Earth's history had just occurred. 96% of marine species went extinct. 70% of terrestrial vertebrates died. Life on Earth was devastated. Recovery would take millions of years. That's when this galactic collision was in the state we observe, 250 million years ago. The galaxies have had 250 million years to continue their merger since then. they're almost certainly fully merged by now. A single large elliptical galaxy probably exists where two spirals once orbited, but we see them as separate, still colliding, because that's how they were 250 million years ago. The mice galaxies, named for their long tidal tails, are about 300 million light-years away. The collision we observe is from 300 million years ago, the Carboniferous period. Vast coal forests covered the land. Giant insects flew through humid swamps. The first reptiles were evolving. Amphibians were the dominant vertebrates. That's Earth, 300 million years ago. And the mice galaxies were in the state we now observe. Their long tails stretching into space as gravity pulled stars away from each galaxy. Stephan's quintet is a group of 5 galaxies that appear close together. 4 of them are actually interacting, about 300 million light-years away. The 5th is much closer, only 40 million light-years away, but appears in the same region of sky from our viewpoint. When you look at Stephan's quintet, you're seeing multiple moments in time. The 4 distant galaxies from 300 million years ago. The nearer galaxy from 40 million years ago. Different eras, different events, all appearing simultaneous because the light arrives at the same time. This is normal in astronomy. Everything you see is from different moments, different distances, different times. The universe is not synchronized. Now let's talk about the cosmic microwave background from a different perspective. The CMB comes from all directions. When we detect it, we're seeing a spherical shell around us. Every point on that shell is the same distance away in terms of light travel time, about 13.8 billion light-years. But because the universe has been expanding, the actual current distance to the surface of last scattering is much larger, about 46 billion light-years. This creates an interesting situation. Different parts of the CMB come from regions of space that are now 92 billion light-years apart from each other. And yet the temperature is almost exactly the same everywhere. Only tiny variations of 1 part in 100,000. This is puzzling because those regions have never been in contact. Light hasn't had time to travel between them, even in the entire age of the universe. So, how did they reach the same temperature? This is one of the problems that led to the theory of cosmic inflation. The idea that the universe underwent a brief period of exponential expansion in its earliest moments. During inflation, regions that were once close together and in thermal equilibrium were pushed far apart. After inflation ended, they were so far apart they could never communicate again, but they retained the same temperature from when they were in contact. This explains the uniformity of the CMB. Anyway, the point is that when we observe the CMB, we're seeing light from regions of space that are incredibly far apart now. We're seeing the entire visible universe as it was in the past. A spherical snapshot from 13.8 billion years ago. And that snapshot surrounds us completely. Everywhere we look, we see this ancient light, the afterglow of the Big Bang, the oldest photons in the universe, still traveling, still arriving at Earth, still showing us the early universe. Now, let's think about time dilation and how it affects observations. Einstein's theory of relativity tells us that time passes at different rates, depending on your motion and the gravitational field you're in. For astronomical observations, this creates some interesting effects. Light traveling from a distant galaxy to Earth is not affected by time dilation in its own reference frame. From the photon's perspective, no time passes at all. The journey is instantaneous, but from our perspective, billions of years pass. The photon experiences the entire journey as a single moment. We experience it as an eon-long voyage across space. Both perspectives are valid. They're just different reference frames. This is one of the strange consequences of relativity. Time is not absolute. It's relative to the observer. Another effect comes from gravitational redshift. Light, climbing out of a gravitational well, loses energy. Its wavelength increases, shifting toward the red end of the spectrum. We see this when we observe light from very massive objects. White dwarfs, neutron stars, black holes, anything with intense gravity. The light we detect is redshifted by gravity. It's been stretched by the effort of escaping the gravitational field. And the more massive the object, the greater the redshift. For a neutron star, the gravitational redshift is significant. Light, leaving its surface, is measurably redder than when it was emitted. For a black hole, the redshift becomes infinite at the event horizon. Light, trying to escape from the event horizon, is redshifted so much it loses all its energy. It never actually escapes. This is why nothing can escape from a black hole, not even light. But we're getting sidetracked. The point is that light carries information about the conditions where it originated. When we analyze starlight, we can determine the star's temperature, composition, motion, and gravitational field, all from light that's been traveling for years or centuries. We're doing stellar archaeology, piecing together information about stars from ancient photons. Now, let's think about proper motion. Stars aren't stationary. They're all moving through space at different velocities. The Sun orbits the center of the Milky Way at about 500,000 miles per hour. Other stars have their own orbital velocities, plus their peculiar motion, their individual motion relative to the average. Over long enough timescales, this motion changes the apparent positions of stars in the sky. This is called proper motion. For nearby stars, proper motion is measurable over years or decades. Barnard's star, about 6 light-years away, has the largest proper motion of any known star. It moves about 10 arc-seconds per year across the sky. That doesn't sound like much, but it means that in about 180 years, Barnard's star moves an angular distance equal to the diameter of the full moon. We can actually see it moving if we compare images taken decades apart. Now, here's the thing. The motion we measure is from the past. The light we see from Barnard's star left 6 years ago. So the position we observe is where the star was 6 years ago. The star has moved since then. It's in a different location now. But we can't see that. We see where it was. For nearby stars, this doesn't matter much. 6 years of motion is small. We can calculate where the star is now based on its velocity. But for distant stars, it becomes more complicated. A star, 1,000 light-years away, might have moved significantly in 1,000 years. The position we observe is 1,000 years out of date. For stars moving perpendicular to our line of sight, this affects their apparent position. For stars moving toward or away from us, it affects their distance. Everything we measure is from the past. Position, distance, velocity, temperature, composition. All of it is historical data. The current state is unknown. Let's talk about one more implication. The observable universe has a finite size. Not because the universe itself is finite, though it might be, but because light has only had a finite time to travel since the Big Bang. The observable universe is about 93 billion light-years across. That's the region from which light has had time to reach us. Beyond that distance, light hasn't had time to arrive yet. Those regions are beyond our cosmic horizon. We can't see them. Not because they don't exist, but because the light hasn't reached us. And due to the accelerating expansion of the universe driven by dark energy, some regions that are currently beyond our horizon will always be beyond our horizon. The expansion is carrying them away faster than light can travel. They're receding faster than the speed of light. Wait, how is that possible? Light speed is the universal speed limit. How can something recede faster than light? The answer is that the speed limit applies to motion through space. Nothing can move through space faster than light. But space itself can expand at any rate. And when space expands fast enough, distant objects are carried away faster than light. This is happening right now. There are galaxies so far away that they're receding from us faster than the speed of light. We can still see them because the light we're receiving left when they were closer, before expansion had carried them so far away. But any light they emit now will never reach us. It's fighting against the expansion, trying to travel toward us, but space is expanding faster than it can travel. The light will never close the distance. Those galaxies are forever beyond our reach. Not just physically, but observationally. We'll never see what they look like now. We can only see their past, from when they were close enough that their light could still reach us. This creates a strange situation where the observable universe will actually shrink in the future. More and more galaxies will be carried beyond the horizon. Their light will stop reaching us. The universe will appear emptier. In the far future, trillions of years from now, intelligent beings looking up at the sky will see very little. Only the galaxies gravitationally bound to their local group. Everything else will have disappeared beyond the horizon. They won't see the cosmic microwave background because it will be redshifted into undetectability. They won't see distant galaxies. They won't have evidence of the Big Bang. They'll think the universe is small, static, eternal, and they'll be wrong. But they'll have no way to know they're wrong because the evidence will be gone. We're fortunate to exist at a time when the universe still reveals its history, when we can still see the CMB, when we can still observe distant galaxies, when we can still piece together the story of cosmic evolution. This window won't stay open forever. Eventually, the evidence will slip beyond the horizon, lost to the accelerating expansion. But for now, we have access. We can look back in time. We can see the early universe. We can trace the history of galaxies, stars, and structure, all because light takes time to travel. All because distance equals time. All because we're always looking into the past. Let's explore a few more specific stars to really drive this concept home. Each one is a window into a different era. Procyon, the brightest star in Canis Minor, is 11.4 light-years away. The light you see left in 2012 or 2013, the London Olympics. The Higgs boson was discovered. Hurricane Sandy hit the East Coast. Barack Obama was re-elected president. That's when this light began its journey. About 11 or 12 years ago. Castor, in Gemini, is about 51 light-years away, as we mentioned earlier. But let's think about what 1973 really means. The first mobile phone call, the end of the Vietnam War, the oil crisis. Skylab was launched. Pink Floyd released Dark Side of the Moon. That was 1973. The world, before personal computers, before the internet, before smartphones. A completely different technological landscape. That's when Castor's light left, 51 years ago. Shaula, the bright star at the tip of Scorpius's tail, is about 570 light-years away. That light is from 1454. Constantinople had just fallen to the Ottoman Turks the previous year, ending the Byzantine Empire. The 100 Years' War between England and France was winding down. Johannes Gutenberg had just invented the printing press. The Renaissance was beginning in Italy. That's 1454, over 5.5 centuries ago. Caus Australis, the brightest star in Sagittarius, is about 143 light-years away. The light you see is from 1881. Billy the Kid was killed that year. President James Garfield was assassinated. The first electric streetcars began operating. Thomas Edison was building power stations. The Old West was ending. The modern industrial era was beginning. That's 1881, 143 years ago. Gacrux, one of the stars in the Southern Cross, is about 88 light-years away. That light is from 1936. The Great Depression was ongoing. The Spanish Civil War began. The Berlin Olympics were held, used as Nazi propaganda. Jet engines were being developed. Television was brand new. That's 1936. 88 years ago, before World War II. Acrux, the brightest star in the Southern Cross, is about 320 light-years away. The light you see is from 1704, the early 18th century. Queen Anne ruled England. Peter the Great was modernizing Russia. Isaac Newton was 72 years old and still scientifically active. The Enlightenment was beginning. That's 1704, 320 years ago. Each of these stars is telling you a different story. Each one is showing you a different moment in human history. And when you look at the sky, you see all these moments at once. A patchwork of different eras, different times, all illuminated by ancient starlight. Now, let's think about binary stars. Many stars exist in binary or multiple star systems. Two or more stars orbiting each other. Albireo, a beautiful double star in Cygnus, is about 430 light-years away. The two stars orbit each other over a period of about 75,000 years. The light we see left Albireo in 1594, late 16th century. The stars have orbited each other for less than 1% of their orbital period since that light left. From our perspective, they've barely moved. But they have moved. The current positions are slightly different from what we observe. We see where they were 430 years ago, not where they are now. Mizar and Alcor, the famous double star in the Big Dipper, are about 83 light-years away. The light is from 1941. World War II was raging. Pearl Harbor was attacked that year, bringing the US into the war. The first computer, the Z3, was completed in Germany. Citizen Kane was released. That's 1941. 83 years ago. Sirius, which we mentioned before, is actually a binary system. Sirius A is the bright star we see. Sirius B is a white dwarf companion, much dimmer but still present. They orbit each other every 50 years. The light we see is from 8.6 years ago. In 8.6 years, they've moved about 1/7 of their orbit. We see them in one configuration, but they're currently in a noticeably different position. We won't see their current position for another 8.6 years. Alpha Centauri is also a binary. as we mentioned. Alpha Centauri, A and B, orbit each other every 80 years. The light we see is 4.37 years old. They've moved slightly in their orbit since then. Not much, but measurably. And we can't see the current position. We see the past. This becomes important for precise astronomical measurements. When astronomers measure the positions of stars for astrometry, they have to account for light travel time. They have to calculate where the star was when the light left, not where it is now. For nearby stars, this is a small correction. For distant stars, it becomes more significant. Everything in astronomy requires accounting for light travel time. Every measurement, every observation, every calculation, because we're always observing the past. Let's think about stellar evolution and how it relates to light travel time. Stars evolve over millions or billions of years. They're born in clouds of gas. They burn hydrogen for most of their lives. They eventually run out of fuel and die. When we observe stars at different distances, we're seeing them at different stages of evolution. But more than that, we're seeing them frozen at specific moments in their evolution. A star, 1,000 light years away, is showing us how it looked 1,000 years ago. It's evolved since then, but we can't see that evolution. We see a snapshot from the past. If we observe the same star 100 years later, we're seeing how it looked 900 years ago. Still in the past, just slightly less past. We're moving forward through the star's timeline, but we're always behind. We never catch up to the present. For a star like the Sun, which lives about 10 billion years, 1,000 years of evolution is negligible. The star doesn't change noticeably. But for massive stars that live only a few million years, 1,000 years might represent a measurable fraction of their lifetime. They might have brightened or dimmed slightly. They might have changed temperature. They might be closer to their eventual explosion. And we can't see those changes. We see them as they were, frozen in time. Eta Carinae is a massive star system about 7,500 light-years away. It's one of the most massive and luminous stars known. In the 1800s, it underwent a great eruption, brightening dramatically and ejecting huge amounts of mass. Astronomers observed this eruption from Earth. But it didn't happen in the 1800s. It happened 7,500 years earlier, around 5,500 BCE, the Neolithic period, when humans were just beginning to develop agriculture. The eruption occurred then, and the light traveled for 75 centuries. It arrived in the 1800s, and astronomers saw it unfold. They watched the star brighten over years, saw it eject material, observed it fade back down. All of this happened 7,500 years ago. They were watching history, delivered by light. Today, when we observe Eta Carinae, we're seeing the aftermath of that eruption. The homunculus nebula, a cloud of gas ejected during the eruption, still surrounds the star. But the nebula we see is from 7,500 years ago. It's had 7,500 years to expand since then. The current nebula is much larger than what we observe. We won't see the current state for another 7,500 years. R136, a 1, is the most massive known star. It's in the Large Magellanic Cloud, about 160,000 light-years away. The star has about 250 times the Sun's mass. It's incredibly hot, incredibly luminous, and it's losing mass rapidly through stellar winds. The R136, a 1 we observe, is from 160,000 years ago. The star has been evolving since then. It's lost a significant amount of mass to stellar winds. It's changed temperature, changed luminosity. It might even be noticeably smaller now than it was then. But we can't see that. We see it as it was 160,000 years ago, when Homo sapiens were just emerging in Africa. Betelgeuse, which we've discussed, might have already exploded. The explosion might have occurred centuries ago, and the light is traveling toward us right now. Or it might explode tomorrow, or 1,000 years from now. We don't know, because we can't see the current state. We only see 550 years ago. And 550 years ago, Betelgeuse was still a red supergiant, still burning. If it exploded 400 years ago, the light will arrive in about 150 years. Our descendants will see it. They'll watch Betelgeuse suddenly become as bright as the full moon. They'll study the supernova intensely, but they'll be studying an explosion from our time, from the 21st century. 400 years in their past. This is the perpetual state of astronomy. Always behind, always seeing the past, never catching up to the present. Let's shift to galaxies again and think about galactic evolution. Galaxies change over billions of years. They merge with other galaxies. They form new stars. Their shapes evolve. When we observe galaxies at different distances, we're seeing them at different stages of evolution. Nearby galaxies show us mature galaxies as they appear in the recent cosmic past. Distant galaxies show us younger galaxies as they appeared billions of years ago. By comparing galaxies at different distances, we can trace galactic evolution. We can see how galaxies have changed over cosmic time. The Milky Way is our home galaxy. We're inside it, so we can't see its overall shape directly, but we can infer what it looks like based on our observations of nearby similar galaxies. The Andromeda galaxy, 2.5 million light-years away, is similar to the Milky Way. It's a large spiral galaxy with a similar mass and structure. When we look at Andromeda, we're seeing what a galaxy like ours looked like 2.5 million years ago. That's essentially the present, cosmologically speaking. 2.5 million years is nothing on the timescale of galactic evolution. Galaxies change over billions of years, not millions. So, Andromeda today probably looks very similar to what we observe. But, for galaxies billions of light-years away, the time difference is significant. Those galaxies have evolved substantially since the light we see left them. The Hubble Deep Field is an image of a small patch of sky. It contains about 3,000 galaxies. Many of them are over 10 billion light-years away. We're seeing them as they were 10 billion years ago. The universe was only about 3.8 billion years old then, less than a third of its current age. The galaxies were younger, smaller, more irregular. Star formation was much more active. Galaxy mergers were more common. The universe was a different place, and we can see that directly. We're not inferring what the early universe was like. We're observing it. We're seeing it with our telescopes. Ancient light showing us how things were. The galaxies in the Hubble Deep Field don't look like that anymore. They've had 10 billion years to evolve. They've merged with other galaxies. They've formed trillions of new stars. They've grown larger and more structured. They probably look like the galaxies we see nearby, mature spirals or ellipticals. But we can't see that. We only see how they were 10 billion years ago. Small, chaotic, actively forming stars. This is one of the most powerful techniques in modern astronomy, observing galaxies at different distances to trace cosmic evolution. we can watch the universe grow up. We can see how structures form and evolve. We can test our theories of galaxy formation against direct observations. All because light takes time to travel. All because distance equals time. All because we're always looking backward through history. Now let's think about dark energy and cosmic expansion from this perspective. The universe is expanding. Space itself is stretching, carrying galaxies apart. The farther away a galaxy is, the faster it's receding. This is Hubble's law. But the expansion isn't constant. It's accelerating. Due to dark energy, a mysterious force we don't understand. Dark energy pushes space apart, counteracting gravity, and the expansion is getting faster over time. We discovered this by observing distant supernovae. Type Ia supernovae have a consistent peak brightness. They're standard candles. By measuring how bright they appear, we can calculate how far away they are. And by measuring their redshift, we can determine how fast they're receding. When astronomers did this in the 1990s, they expected to find that the expansion was slowing down. Gravity should be pulling galaxies together, slowing the expansion. Instead, they found the opposite. Distant supernovae were farther away than expected based on their redshift. The expansion had accelerated since the light left. Space had expanded faster than predicted. This was shocking. It led to the discovery of dark energy and won the Nobel Prize. But think about what this means in terms of light travel time. The supernovae they observed were billions of light years away. The light had been traveling for billions of years. During that time, space had been expanding. The galaxy containing the supernova had been carried farther away, so the distance we measure is not the distance when the light was emitted. It's the current distance, accounting for expansion. The light travel distance is how long the light has been traveling. The co-moving distance is where the galaxy is now, accounting for expansion. These are different numbers. For very distant objects, the co-moving distance can be much larger than the light travel distance. A galaxy whose light has been traveling for 12 billion years might now be 30 billion light years away. Space has been expanding the whole time the light was in transit. This makes cosmic distances complicated. We have to specify which distance measure we're using. Light travel distance, which corresponds to time. Co-moving distance, which corresponds to current physical separation. Angular diameter distance, which relates to how large the object appears. Luminosity distance, which relates to how bright the object appears. All different, all useful for different purposes. But they all arise from the same fundamental fact. Light takes time to travel, and space is expanding during that time. We're always seeing the past, but the past is from a universe that was smaller than it is now. Let's think about the edge of the observable universe. The most distant objects we can see are about 13.8 billion light-years away in terms of light travel time. That's how long the light has been traveling. But those objects are now about 46 billion light-years away due to expansion. They're at the edge of our cosmic horizon, just barely within our observable universe. If we wait a billion years, we'll see objects that are currently beyond our horizon. Their light will have had more time to reach us. The observable universe will have grown, but it won't grow as much as you might think, because the expansion is accelerating. Some objects that are currently receding slower than light will eventually cross the threshold and begin receding faster than light. Once they do, their light will never reach us. They'll slip beyond the horizon, permanently. The observable universe will still grow for a while, but then it will start to shrink. More and more galaxies will be pushed beyond the horizon by accelerating expansion. Eventually, in the far future, we'll only see our local gravitationally bound group. Everything else will have disappeared, and any light emitted by those distant galaxies after they cross the horizon will never arrive. We'll forever see them as they were the moment they crossed the threshold. Frozen in time, receding away, fading from view, and then gone, invisible forever. This is the ultimate consequence of light travel time combined with cosmic expansion. There are parts of the universe we will never see, not because they don't exist, but because the light will never have time to reach us before expansion carries them too far away. The universe is larger than the observable universe, probably much larger, possibly infinite. But we can only see a finite portion, the portion from which light has had time to reach us. Everything else is beyond the horizon, invisible, unknowable, at least through direct observation. Now, let's return to a human scale one last time. Let's think about what all this means for how you see the night sky. When you go outside tonight and look up, you're seeing thousands of stars. Each one is a different distance. Each one is showing you a different moment in time. The closest stars, like Alpha Centauri, are showing you the very recent past, a few years ago. Nothing has changed. The stars look the same as they did then. Stars like Sirius and Vega are showing you the past decade or two. Recent enough that if you're old enough, you remember those years. You can think back to what you were doing then, where you lived, what your life was like. And the light you see from those stars is from that time, from when you were younger, when the world was different. Stars like Aldebaran and Pollux are showing you decades ago, before you were born, probably, from your parents' generation, from a world that still seems recognizably modern, but different in countless ways. Stars like Rigel and Polaris are showing you centuries ago, the Renaissance, the Age of Exploration, the early modern period, a world that seems foreign to us. No electricity, no modern medicine, no technology as we know it, but recognizably human, recognizably our civilization. Stars like Deneb and Antares are showing you millennia ago. Ancient civilizations, Rome, Greece, Persia, China, empires that rose and fell, the foundations of our culture being laid. All of this is visible simultaneously in the night sky. Different eras, different worlds, different moments in history, all illuminated by starlight that's been traveling for different amounts of time. The sky is a tapestry of time, a visual representation of history, and you have access to it just by looking up. No telescope needed for the bright stars, just your eyes and a dark sky, and the ability to understand what you're seeing. Because once you understand light years, once you grasp that distance equals time, the night sky transforms. It's no longer just pretty lights scattered across darkness. It's a timeline, a museum of cosmic and human history. Every star, an exhibit showing a different era. Every constellation, a collection of moments from different times. The universe showing you where it's been and where we've been. Because human history is woven into this cosmic timeline. The light from distant stars carries images of Earth from different eras. If someone were observing from those stars, they'd see our past. From Sirius, they'd see Earth from 8.6 years ago. From Rigel, they'd see Earth from the Middle Ages. From Deneb, they'd see ancient Greece. We're connected to the stars, not just by light, but by time. Our past is visible to hypothetical observers around distant stars. Their past is visible to us. We're all embedded in this web of light and time, all seeing each other's history, all connected by photons traveling across the cosmos. This is the profound truth that light years reveal. Distance and time are the same thing in astronomy. You can't separate them. Every distance measurement is simultaneously a time measurement. Every observation is simultaneously a glimpse into the past. The universe doesn't exist in a single moment. It's spread across time, with different regions visible at different eras. And we're here, now, able to observe all these different eras at once, able to piece together the story, able to understand our place in cosmic history. This is the gift of light years. This is why they matter, not just as a convenient unit of measurement, but as a window into the nature of reality itself. Time and space intertwined. The past always present in our observations. The present always invisible beyond our reach. And the future unknowable, hidden behind the light that hasn't arrived yet. This is the universe we live in. A universe where looking far away means looking far back, where every star tells a story from the past, where the night sky is a time machine showing us cosmic history. This is what light years mean. This is what they reveal. And once you understand it, you can never look at the stars the same way again. But there's even more to explore about what this means. Let's think about specific constellations and how each one is a collection of different moments. Orion is one of the most recognizable constellations in the night sky. It dominates the winter sky, visible from both hemispheres. The constellation contains stars at vastly different distances. Betelgeuse, the red giant marking the shoulder, is about 550 light-years away. Rigel, the blue giant marking the foot, is about 860 light-years away. Bellatrix, on the other shoulder, is about 250 light-years away. The three stars of Orion's belt, Alnitak, Alnilam, and Mintaka, are at different distances. Alnitak is 815 light-years away. Alnilam is 2,000 light-years away. Mintaka is 915 light-years away. When you see Orion, you're seeing stars from different centuries and millennia. Betelgeuse, from the late 1400s. Rigel, from the early 1200s. Bellatrix, from the 1700s. The belt stars from various dates spanning over 1,000 years. The constellation, as a pattern, only exists from our viewpoint. From elsewhere in the galaxy, these stars would be scattered across the sky in completely different arrangements. And from our viewpoint, we're seeing a composite image of different eras. The Big Dipper is another famous pattern. All 7 main stars are at different distances. Dubhe, at the front of the bowl, is about 124 light-years away. Merak, at the back of the bowl, is about 79 light-years away. Phecda, at the bottom of the bowl, is about 84 light-years away. Megrez, where the handle meets the bowl, is about 80 light-years away. Alioth, in the middle of the handle, is about 81 light-years away. Mizar, second from the end of the handle, is about 83 light-years away. Alkaid, at the end of the handle, is about 104 light-years away. The stars in the bowl and handle are relatively close together in distance, between 79 and 84 light-years. They're showing us the 1940s. World War II, the beginning of the nuclear age, the early computer era. But Dubhe and Al-Qaeda are farther away. Dubhe is showing us 1900, the turn of the 20th century. Al-Qaeda is showing us 1920, the roaring 20s. When you look at the Big Dipper, you're seeing mostly the 1940s with a couple of stars from the early 1900s and 20s. A snapshot of the first half of the 20th century. The Southern Cross, visible from the southern hemisphere, has 4 main stars. Acrux is about 320 light-years away, showing us the early 1700s. Bicrux is about 270 light-years away, showing us the mid-1700s. Gaycrux is about 88 light-years away, showing us the 1930s. Delta Crucis is about 360 light-years away, showing us the mid-1600s. Each constellation is a time capsule, a collection of stars from different eras, all appearing to form a pattern from our perspective. Let's think about nebulae and how light travel time affects our observations of them. The Orion Nebula is about 1,350 light-years away. It's a massive cloud of gas and dust where new stars are forming. When we observe it, we're seeing the nebula as it was in the late 6th century. Around 670 CE, the early Middle Ages. The nebula has been evolving since then. New stars have formed. Stellar winds from young hot stars have pushed gas around. The structure has changed, but we see it as it was 1,350 years ago. The current nebula is probably noticeably different. More stars have formed. The gas has been sculpted by stellar winds and radiation, but we won't see that for another 1,350 years. The Carina Nebula is about 7,500 light-years away. The nebula we observe is from around 5,500 BCE, the Neolithic period. This nebula contains Eta Carinae, which we discussed earlier. When we see the nebula and the star together, we're seeing both as they were 7,500 years ago. The Ring Nebula is about 2,300 light-years away. It's a planetary nebula, the remnant of a sun-like star that shed its outer layers. We see it as it was around 300 BCE. Ancient Greece. Aristotle was alive. Alexander the Great had died only about 20 years earlier. The nebula has been expanding for the past 2,300 years since that light left. It's larger now than what we observe, but we see the earlier, smaller version. The Helix Nebula is about 650 light-years away. We see it as it was around 1374, the late Middle Ages. The Black Death had swept through Europe only 25 years earlier. The nebula has expanded for 6.5 centuries since then. Every nebula we observe is a snapshot from the past. The current state is unknown, invisible, hidden behind the light travel time barrier. Let's think about star clusters. The Pleiades, also called the Seven Sisters, is an open cluster about 440 light-years away. The cluster contains over 1,000 stars, though only 6 or 7 are easily visible to the naked eye. We see the cluster as it was around 1584, the late Renaissance. Queen Elizabeth I ruled England. Shakespeare was 20 years old. Ivan the Terrible had just died in Russia. The cluster has evolved slightly since then. The stars have moved in their orbits around the cluster's center of mass. Some stars have been born, though star formation in the Pleiades is mostly finished, but we see it as it was over 400 years ago. The Hyades is another open cluster, about 150 light-years away. We see it as it was in the late 1800s, about 1874. The Victorian era. The telephone had just been invented. The light bulb would be invented 5 years later. The automobile was still decades away. That's the Hyades we see. Messier 13, the great globular cluster in Hercules, is about 25,000 light-years away. We see it as it was 25,000 years ago, the last ice age. Neanderthals still existed. Homo sapiens were hunter-gatherers. No agriculture, no cities, no civilization. That's Earth 25,000 years ago. And the cluster has been evolving for all that time. Stars have orbited the cluster's core. Some stars have collided and merged. The cluster has interacted gravitationally with passing molecular clouds. All of this has happened since the light we see left, but we can only see the cluster as it was 25 millennia ago. Omega Centauri, the largest globular cluster in the Milky Way, is about 17,000 light-years away. We see it as it was 17,000 years ago. The end of the last ice age. Sea levels were much lower. The Bering Land Bridge connected Asia and North America. Humans were just beginning to spread across the Americas. That's the Earth that existed when this light left Omega Centauri. And the cluster, containing about 10 million stars, has been evolving ever since. Now, let's think about what happens when we observe the same object multiple times over years or decades. Astronomers have been observing certain objects for over a century. They have images from the late 1800s and early 1900s, and they have modern images from today. When they compare these images, they can sometimes see changes, not real-time changes in the object, but changes in what era of the object's history they're observing. For a nebula expanding at 10,000 miles per hour, you might think you could see the expansion over a century. And you can, sort of. But it's complicated by light travel time. Imagine a nebula, 1,000 light-years away, in 1900. You observe it as it was in the year 900. In 2000, you observe it as it was in the year 1000. You've moved forward 100 years through the nebula's timeline. The nebula has expanded during those 100 years of its history. But the nebula's current state in the year 2000 is still unknown. You're seeing it as it was in 1000, not as it is in 2000. You won't see its 2000 state until the year 3000. This can be confusing, but it's the reality of astronomical observation. You're always looking into the past, and observations separated by time are seeing different moments in the object's history, but they're still in the past. Let's think about the practical implications for astronomy as a science. Every measurement has to account for light travel time. When you measure a star's position, you're measuring where it was when the light left. When you measure a galaxy's distance, you're calculating how far away it was when the light left, though space has expanded since then. When you measure a supernova's brightness, you're measuring how bright it was when it exploded, not how bright the remnant is now. All data is historical data. There's no such thing as a real-time observation in astronomy, except for objects in our solar system, where light travel time is measured in minutes or hours. This creates interesting challenges for astronomy. How do you study the current universe when you can only observe the past? The answer is that you can't study the current universe directly. You can only observe the past and use physics to predict the present. For nearby objects, this is easy. A star, 50 light-years away, hasn't changed much in 50 years. Its current state is probably almost identical to what we observe. For distant objects, it's much harder. A galaxy 10 billion light-years away has had 10 billion years to evolve. Its current state could be completely different from what we observe. We have to use our understanding of galaxy evolution to model what it probably looks like now. But we can't confirm our models. We won't see its current state for another 10 billion years. This is both a limitation and an opportunity. It's a limitation because we can never directly observe the current state of distant objects. But it's an opportunity because we can observe cosmic history directly. We can see how galaxies looked at different ages. We can trace their evolution by comparing objects at different distances. We can test our models of cosmic evolution against observations of the past. No other science has access to its subject's history like this. Biologists can't observe ancient life directly, only through fossils. Geologists can't see ancient Earth, only evidence left in rocks. But astronomers can literally see the ancient universe. They can observe galaxies as they were billions of years ago. They can watch cosmic history unfold. All because light takes time to travel. Let's think one more time about the cosmic microwave background and what it represents. The CMB is light from the surface of last scattering, 380,000 years after the Big Bang. That light has been traveling for 13.8 billion years. It's crossed almost the entire observable universe. And it's still arriving at Earth. Every day, new CMB photons enter our detectors. Photons that have been traveling since the early universe. They've crossed billions of light-years of expanding space. They've been redshifted from visible light to microwaves by the expansion. They carry information about the early universe encoded in tiny temperature variations, and they're all around us, coming from every direction, filling the sky with this ancient light. The CMB is the ultimate time capsule. It's showing us the universe at its earliest observable moment, before stars, before galaxies, before structure. Just a hot, dense, nearly uniform soup of matter and radiation. And we can see it. We can map it. We can analyze it. We can learn from it. All because those photons have been traveling for 13.8 billion years, delivering information from the dawn of time. This is extraordinary when you really think about it. We're seeing the birth of the universe. Not through inference or theory, but through direct observation. Ancient light showing us how it all began. Now, as we wrap up, let's think about what all of this means philosophically. The universe doesn't have a universal now. Different locations experience time at different rates depending on gravity and motion. And observers at different locations see different pasts when they look at each other. There's no synchronized moment that encompasses the entire universe. No cosmic clock ticking away the same time everywhere. Time is relative, and what we observe is always the past. This means that our concept of the present is local. The present exists here, now, where we are. But everywhere else, we only see the past. The farther away we look, the deeper into the past we see. And the present, at those distant locations, is invisible to us, hidden behind the light travel time barrier. This is a profound insight into the nature of reality. The universe is not a three-dimensional space that exists in the present moment. It's a four-dimensional space-time, where space and time are inseparably linked. And our observations are always of the past, with the degree of pastness increasing with distance. This is what light years reveal. Not just a convenient measurement of astronomical distances, but a window into the fundamental nature of the cosmos. Distance and time are the same thing. Looking far away means looking far back. The night sky is a museum of cosmic history, and we're privileged to observe it, to study it, to learn from it. This is the gift of light years. This is what makes astronomy unique among the sciences. This is why every star you see is already history. Let's talk about a few more fascinating examples that really emphasize this point. Mu Cephei, also called the Garnet Star because of its deep red color, is about 6,000 light-years away. That light is from around 4000 BCE. The Bronze Age was beginning in the Near East. The first cities were being built in Mesopotamia. Writing was being invented. The pyramids of Egypt wouldn't be built for another 500 years. That's 6,000 years ago. And the light from Mu Cephei has been traveling ever since. VY Canis Majoris is one of the largest known stars. It's about 3,900 light-years away. The light you see is from around 1876 BCE, the Middle Bronze Age. The Minoan civilization was flourishing on Crete. The Shang dynasty would soon rise in China. The Vedic period was beginning in India. That's nearly 4,000 years ago. UY Scuti, another contender for largest known star, is about 9,500 light-years away. That light is from 7500 BCE, the Neolithic period. Agriculture had spread across the Middle East and into Europe. Early farming communities were establishing themselves. The wheel hadn't been invented yet. That's 9,500 years ago. Pistol Star, one of the most luminous stars known, is about 25,000 light-years away. The light you see is from the Ice Age. Woolly mammoths roamed the earth. Humans were hunter-gatherers, living in small bands. Cave art was being created in Europe. That's how far back you're looking when you observe the Pistol Star. LBV 1806 to 20. Another extremely luminous star is about 38,000 light-years away. That light is from 38,000 years ago. Neanderthals were still alive. Homo sapiens had spread across Africa, Europe, and Asia. The Americas were beginning to be populated. Stone tools were the cutting edge of technology. That's the world that existed when this light left that star. Every star I've mentioned is showing you a different moment in time, a different era of human or pre-human history. And all of these moments are visible simultaneously in the night sky. You can see the Ice Age and the Bronze Age and the Middle Ages and the Renaissance all at once, just by looking at different stars. Each one, a time capsule showing a specific era. Let's think about pulsars and how light travel time affects our observations of them. Pulsars are rapidly rotating neutron stars that emit beams of radiation. As the star rotates, the beam sweeps across space like a lighthouse. If Earth happens to be in the path of the beam, we detect regular pulses. The Crab pulsar is in the Crab Nebula, about 6,500 light-years away. It rotates about 30 times per second. When we detect its pulses, we're seeing pulses from 6,500 years ago. The pulsar is still rotating right now, still emitting pulses. But those current pulses won't reach us for another 6,500 years. We see the pulses from 7,500 BCE. The pulsar has rotated about 6 trillion times since those pulses left. 6 trillion rotations we haven't seen yet. they happened, but the light is still traveling toward us. PSRB 1937 plus 21 is one of the fastest spinning pulsars known. It rotates 642 times per second. It's about 16,000 light-years away. The pulses we detect left 16,000 years ago. The pulsar has rotated about 320 trillion times since then. All of that has happened, but we can't see it yet. We see it as it was during the Ice Age, rotating 642 times per second. This is true for all variable objects. Cepheid variables pulsating, eclipsing binaries, orbiting, pulsars rotating, active galactic nuclei flickering. Every variation we observe happened in the past. The current state is unknown. Let's talk about gravitational lensing and how it's affected by light travel time. When light from a distant galaxy passes near a massive object, like another galaxy or a galaxy cluster, the gravity bends the light. This can create multiple images of the same distant galaxy. The light takes different paths around the massive object. Some paths are longer than others. So light traveling different paths left the source galaxy at different times. When we see multiple images of a gravitationally lensed quasar, we're seeing the quasar at different moments in its past. One image might show the quasar as it was 10 billion years ago. Another image might show it as it was 10 billion years plus a few days or weeks ago. The time delay between different images can be measured. This has been used to measure the expansion rate of the universe. By watching the quasar vary in brightness and noting the time delay between when the variation appears in different images, astronomers can determine how much longer one light path is than the other. This, combined with the geometry of the lensing system, allows them to calculate cosmic distances and the Hubble constant. But all of this is observations of the past. The quasar, as it was billions of years ago. The lensing galaxy, as it was billions of years ago. Multiple snapshots from the distant past, arriving at Earth along different routes. Let's think about fast radio bursts, or FRBs. These are mysterious, incredibly powerful bursts of radio waves. They last only milliseconds, but release as much energy as the sun emits in days or weeks. Most FRBs come from billions of light-years away. When we detect an FRB, we're detecting an event from billions of years ago. Whatever caused it, a neutron star collision, a magnetar flare, or something else we don't yet understand, happened in the distant past. The universe was younger, galaxies were different, and something created this burst of radio waves that traveled across billions of light-years to reach us. FRB 121102. One of the first repeating FRBs comes from a galaxy about 3 billion light-years away. The bursts we detect happened 3 billion years ago, the Proterozoic eon on Earth. Simple multicellular life was just evolving. Complex life didn't exist yet. The Earth was dominated by bacteria and simple algae. That's when these radio bursts were emitted. And they've been traveling ever since, crossing 3 billion light-years of expanding space. We're detecting ancient cosmic explosions, delivered to us by radio waves traveling at light speed. Now, let's think about black holes and how we observe them. Black holes themselves don't emit light, but the material falling into them heats up and emits radiation, and the environment around black holes can be incredibly bright. When we observe a black hole, or rather, the accretion disk and jets around it, we're seeing it as it was in the past. M87, the supermassive black hole at the center of the galaxy. M87 is about 55 million light-years away. It's the black hole that was imaged by the Event Horizon Telescope in 2019. The image shows the black hole as it was 55 million years ago, the Paleogene period. Early primates were evolving. The Himalayas were forming. Mammals were diversifying after the extinction of the dinosaurs. That's the black hole we see in the image. It's had 55 million years to evolve since then. Matter has continued falling in. The accretion disk has changed. The jets might have varied in strength. But we can only see it as it was 55 million years ago. Sagittarius A, the supermassive black hole at the center of our Milky Way, is about 26,000 light-years away. When we observe it, we're seeing it as it was 26,000 years ago. The black hole exists right now at the center of our galaxy, but we can't see its current state. We see it from 26 millennia in the past. If something dramatic happened there right now, like a star being torn apart and consumed, we wouldn't see it for 26,000 years. Let's talk about cosmic rays and how they relate to light travel time. Cosmic rays are high-energy particles, mostly protons, traveling through space at nearly the speed of light. When they hit Earth's atmosphere, they create showers of secondary particles that we can detect. These cosmic rays come from various sources. Some from the Sun, taking about 8 minutes to reach us. Some from supernovae in the Milky Way, taking hundreds or thousands of years. Some from active galactic nuclei in distant galaxies, taking millions or billions of years. When a cosmic ray hits Earth, it's been traveling for however long it took to cross the distance from its source. A cosmic ray from a supernova 1,000 light-years away has been traveling for 1,000 years. It was created when the supernova exploded, and it's been flying through space ever since. When it finally hits Earth's atmosphere, it's a messenger from that ancient explosion. The highest energy cosmic rays we detect probably come from the most distant sources. Some might come from quasars, billions of light-years away. Those particles have been traveling for billions of years. They're older than complex life on Earth. They were created in the early universe and have been flying through space ever since. When they finally arrive at Earth, they're delivering energy from the distant past. Let's think about neutrinos from supernovae. When a massive star explodes, it releases an enormous burst of neutrinos. These ghostly particles barely interact with matter and can travel through the entire star without being absorbed. SN 1987 A, the supernova in the Large Magellanic Cloud, emitted a burst of neutrinos. Those neutrinos were detected on Earth a few hours before the light from the supernova arrived. Why? Because the neutrinos escaped from the collapsing core immediately. The light had to work its way out through the star's outer layers, which took hours. But both the neutrinos and the light had been traveling for 168,000 years across the distance from the Large Magellanic Cloud to Earth. When the neutrinos hit detectors on Earth in February 1987, they were delivering information about a supernova that had exploded 168,000 years earlier. Every observation carries information from the past. Even observations that seem instantaneous, like detecting cosmic rays or neutrinos, are actually detecting particles or radiation that has been traveling for years, centuries, or millennia. Let's return once more to thinking about the night sky as a whole. The Milky Way itself, the band of light stretching across the sky, is a composite image of stars at different distances. The nearest stars in the Milky Way band are hundreds of light-years away. The farthest visible stars are tens of thousands of light-years away. you're seeing centuries to millennia of history spread across that luminous band. The dark lanes in the Milky Way, regions where dust blocks the light from distant stars, are showing you the dust as it was centuries or millennia ago. That dust has moved, evolved, been pushed by stellar winds, but you see it as it was when the light left. Every feature you observe in the night sky is historical. The shapes of constellations, the brightness of stars, the positions of planets, the appearance of nebulae, all of it is from the past. Nothing you see in the sky exists in the state you're observing it. Everything has changed, evolved, moved on, but the light carrying the old information is still arriving, still showing you how things were. This is the fundamental nature of astronomical observation. This is what light years teach us. Distance equals time. Space and time are linked. The universe reveals its history through light. And we're fortunate enough to be here, now, able to observe it, to study it, to learn from it. This understanding transforms how we see the cosmos. It's no longer just a collection of objects in space. It's a timeline, a historical record, a museum of cosmic evolution. Every observation is an archaeological discovery. Every photon is an artifact from the past. And we're the archaeologists, piecing together the story of the universe from these ancient messengers. This is what makes astronomy so profound. It's not just studying distant objects, it's studying the history of everything. The evolution of stars, galaxies, and the entire cosmos, all revealed through the simple fact that light takes time to travel. This is the gift of light years. This is the power of understanding that distance and time are connected. This is what makes astronomy possible. Thank you for joining me on this journey through space and time. If you found this exploration valuable, a like or subscribe would mean the world to me. And remember, every time you look up at the stars, you're not seeing the present. You're seeing the past. You're witnessing history. The universe is showing you where it's been, one light year at a time. Good night, and may you never look at the stars the same way again.